Hello, friends. You're most welcome to my command center. I am in space and exploring the nearby space time. And whenever we want to explore the space, we use these sensitive equipment like telescopes and different types of telescopes. But we cannot appreciate if it is not an optical telescope. We suppose we use X-ray telescope, then it is a different device, and it is not at all nice to look at until and unless you convert that image into a visual image. So I think the optical telescopes have a very profound place in our exploration, and today I would like to draw your attention to something which is naturally available, and this phenomena can be used to look at far off object, and this process is called gravitational lensing. We will understand this in our discussion today, but before we start, let us understand how telescope work very briefly. So if you look at the telescope, it has in a simple telescope, it is like a tube, and you can see that from one side the light enters, and then using a couple of lenses, glass lenses, you try to focus it on in your eye. So the whole logic behind a telescope is that you use glass lens to converge the light. However, the idea is that you gather more light from a distant object and focus it in a very narrow point, which is called the focal point. So the objective of doing this is that since you are gathering a lot of light and then focusing on a small point, and then you put your eye on that point, you start seeing that object from which the light is coming much closer to you. That is the whole idea of this whole concept of increasing the magnification of a far off object using telescope. But in this these are the first telescopes which were invented by the various physicists. But there was a drawback in these telescopes, because when the light passes through the glass, it gets distorted because the glass will offer some sort of resistance to the light, and therefore there will be a some aberration, and there will be a little bit of obstruction also. So because of these factors, the new type of telescope which was invented later, and by the way, these telescopes are called refracting type telescope. But then instead of using the lenses, the scientists replaced them, changed the design a little bit, and started using something like this. This is a reflecting type telescope where some of the distortion can be sorted out. However, these are not perfect. The idea being that more light enters the tube, and then instead of using a convex lens to narrow the beam towards a focal point, here you are actually using a concave mirror, not a lens. So it will focus the light which is entering the tube on a central point, and there you actually put the eyepiece or your gadgets to examine it. The challenge here is that the central part of that image will always be hidden from you, the central point of the star that you're trying to see at from a far out distance. So there are a lot of pros and cons for both designs, and that is why scientists have come out with better designs of telescope which requires lot of techniques and very high precision. And whenever we talk high precision, the cost goes up. For example, James Webb telescope, it has taken 30 years to construct, and the cost of the telescope runs into billions of dollars. So there is always a trade-off. But did you know that there is something called gravitational lensing, which is naturally available? And using this natural phenomena, we can actually see far off objects, and we can see them clearly in the optical wavelength without using any X-ray telescope or infrared telescope or any different type of telescope. All we need to do is understand how this gravitational lensing works. Gravitational lensing works in the pretty much in the same manner, which involves bending of light. So as you know that the large amount of gravity can also affect the photons of the light. The photons are affected by only gravity as a force, and therefore when the light is passing in a straight line, and if they are passing through a strong gravitational body which has a lot of gravity in it, or a bigger mass, the light tend to bend because of this effect of the gravity. That was first proven when during a solar eclipse during the 50s, that the sun was actually bending the light coming from the star behind it. So this phenomena is very well known, and scientists also know that you can actually use the gravity to see the far off object behind this high gravitational area. So now if there is a galaxy cluster, the combined gravity of the galaxy cluster can act as your lens, because anything behind the galaxy cluster, the light when it is approaching you, it will bend and come towards you, as I'm trying to show in this image. And when you're able to gather that light, more light about the object will come near you. That means you can see it and examine it. So this is the concept of the gravitational lensing, and it's very effective. You can actually keep increasing the size of the area or the mass behind which you want to see. You can actually identify a star, or you can identify one galaxy and you want to see another galaxy behind it, or you can identify a few galaxies or a cluster of galaxies, or even larger objects, even large collection of galaxies, and use them as your lens. So you don't have to really construct very expensive high precision equipment to see far off places. You can use the natural phenomena which is available for us to examine the space, especially the far off objects, and examine them up close, because the gravity itself will help us and bring those images closer to us, and can act as a big telescope which is just floating around in space. And then the best part is you can change your target, and you can start examining things wherever you want to. The only drawback is that image will look like this. The image of these far off object will be little distorted, and it will come like a rim. And this rim is also first described by Einstein. Also there is a similar ring in the black hole also when the light comes. So the light of the body which is behind this particular galaxy cluster will tend to bend, but also get distorted. So what we have to do is, we have to, when we are examining this using the galaxy cluster as a lens for ourselves, in our receiving end we have to just know with what angle this light is bending and apply the correction, and that way we can actually recreate that image very easily using our earth-based equipment. So by this method, by gravitational lensing method, we don't have to spend a lot of money in building bigger and larger telescope, because these natural telescopes are already available. All we need is basically to understand this phenomena and use our smaller telescope to examine these images, and probably use software to correct because of this gravity, recreate the image using the software, and then we can see far off object. And that this technique has been very helpful. And there is a limit to how many telescopes we can build. We have started about 200 years back, or maybe 300 years back, when we started building large telescopes. But building large telescope requires very high precision, lot of glass maybe. Now today we are not using glass, like for example in James Webb, but we are using those rare earth elements which are very rare. That is why they are called rare earth. So we are using those kind of materials which are quite expensive. We are also doing a gold coating of the glasses. As you can see, the James Webb is in infrared. So there is a limit to how many expensive telescopes mankind can build. So I think the solution lies in looking at cosmos up close, using the natural phenomena, and use a smaller telescope to understand what is going on from in larger bodies, and examining them up close using this gravitational lensing phenomena or the processes. So friends, this is something I wanted to discuss on my live stream today in the multiverse section. And so if you have any suggestions, you please share your comments and thoughts. Otherwise, I'll take your leave today, and I'd just like to say bye today, and only to catch you again tomorrow. Until then, please take care, and catch you tomorrow again in the latest finding in space-time on Akulmach. Bye bye for today.